Integration by parts. Integral u dv equals uv minus integral v du. Integration by parts is for integrands that have different kinds of functions. The choice for u is based upon liate. Logarithm, where du could simplify the integrand. Inverse trigonometry. Algebraic, polynomial. Trigonometric, exponential, where dv would be easy to integrate. We use product rule to find the integration by parts formula. There is this formula for definite integrals, though it's easier just to find the difference between the antiderivatives. The upcoming slides are for the following easy integrals. Here. We won't be doing 1. Integrals like integral x squared e to the x dx that have repeated integration by parts, nor 2. Integrals like e to the x sine x dx that have solving for integrals. Integral x sine x dx, integral x ln x dx, integral x e to the x dx, integral ln of x dx equals x ln x minus x plus c. Integral inverse tangent of x dx, before we do partial fraction decomposition, just because we have a rational function doesn't mean we use partial fractions. Consider simple, simple division, simplification, long division, and substitution, where we have the following. For the long division, note that this. Another example of division is this. Partial fractions. Consider this integral. First factor the denominator. We split up the fraction, but we don't know the numerators. To find the values of a and b, consider multiplying by the denominator. If x equals 0, then b's coefficient is 0, and we'll find a. With x equals minus 1, we'll find b. Having separated the fractions and found the numerators, we integrate. Generally, for some questions, logarithmic identities are used a lot. Improper integrals. Let's consider integrals where the limits or integrands go to infinity. For these improper integrals, we cannot substitute infinity in calculations. We have to transform the integral into a limit and take that limit to infinity. If the limit exists, then the integral is convergent. Otherwise, it's divergent. Here are the integrals. And we should get the following. For these improper integrals, we cannot substitute values that will result in undefined in calculations. We have to transform the integral into a limit and take that limit to that value based upon how we approach it. If the limit exists, then the integral is convergent. Otherwise, it's divergent. Here are the integrals. And we should get the following. If we generalize the exponents, we would get the following. This and that. Here are functions and improper integrals. Note that if it's bigger than something that diverges, then it diverges. And if it's smaller than something that converges, then it converges. The idea doesn't work in reverse. That is, if it's bigger than something that converges, it may or may not converge. And if it's smaller than something that diverges, then it may or may not diverge. We need non-negative functions since that lower bound squeezes the integral. For improper integrals with integration by substitution, integral 1 to infinity x squared e to the negative x to the power 3 dx. We get the following. We'll call integration by substitution. And here are the calculations. We call a limit x to 0 from the positive side, ln x equals minus infinity. And so it has a vertical asymptote of x equals 0. For improper integrals with integration by parts, integral 0 to 1 ln x dx. We get the following. We call integration by parts. We get the following. Need L'Hopital's rule to do the first limit. And we get the following. Or improper integrals with integration by partial fractions. Integral 1 to infinity 1 over x squared plus x dx. We get the following. We call integration by partial fractions. And we get these calculations. Nuance about divergence. Regarding convergent and divergent integrals, convergent and convergent is convergent. Convergent and divergent is divergent. Divergent and divergent is inconclusive since it could either converge or diverge. The first integral diverges, but the second integral converges. Divergence doesn't mean positive, negative infinity. For example, note the oscillation. And we get the following. Nuance about double infinities. If both this and that integral converges, then we can define this. Generally, this is not the same as that. On the next slide, we'll consider the example of f of x equals sine of x. On the left side, I note that cosine x equals cosine minus x since cosine x is even. And we get the following. On the right side, note that neither of these integrals converge. And we get the following. We showed that the latter integral diverges. The former integral diverges due to oscillation. And we get the following. Splitting techniques. For limits with infinity, we can split up a finite and infinite part. For integrands with discontinuity at c on an interval where a is less than c less than b, we can split up the interval as long as the integrals are convergent.